Hello everybody and welcome to the NPTEL online certification course on microelectronics devices and circuits. In our previous discussion on our lecture and previous module, we have understood how your BJT acts as a switch as well as an amplifier, and where should we bias our device so that the device works as an amplifier. In this slide we continue with the same thing which we have left in the previous one, that we see that in a common emitter mode configuration, if you have a common emitter mode configuration BJT, right, then you have RC here, right, you have VCC, and then you will have this. So, for a common emitter mode configuration you will have this, and then there will be a bias given here, and this bias will bias the device at a particular appropriate Q point. Let us see how do I do that. Assuming so I get, if you go back through this table, this is basically your VCE. So, I get VCC equals to IC RC plus VCE, right. So, you see VCC equals to ICRC plus VCE. Therefore, if you want to make ICRC one side, I get ICRC equals to VCC minus VCE. So, as I discussed with you, IC will be therefore equals to VCC by RC minus VCE by RC. So, now if you plot a graph of let us say on this side you have got IC, right, and on this side you have got VCE, right. Now, putting the same equation in this one, if you look at the x axis, your IC will be equals to 0 in that case. So, when IC equals to 0, I get VCE or VCE to be equals to VCC. So, what I can point out is that this is the VCC point, right, and then on the y axis your VCE will be equals to 0. So, at x axis, right, IC equals to 0, place it into this equation and you get VCE equals to VCC. This is the first thing which you get, and you place a point here. The second point is that at y axis I get VCE to be equals to 0. As I get VCE to be equals to 0, I can safely write down this to be as IC to be equals to VCC by RC. So, I put a point here which is basically VCC by RC. Now, simply join these two lines and we define this to be as the load line. I will explain to you why is it known as load line. So, it is a load line whose slope is incidentally equals to minus 1 by R, fine, which means that if the resistance 1 by RC, actually this RC is this collector resistance. So, depending upon the collector resistance, the slope of this line will change, right. Now, wherever it cuts the IV characteristics of the device, we define that to be as the Q point, and those are the possible points where you will get the Q point. So, if you have I versus V characteristics here, that is a good idea to plot it first of all like this, and I get something like this. Then I get this to be possibly a Q point, because within the active region this Q point seems to be further away from saturation as well as from cutoff. So, this is my cutoff point, this is my active, and this is saturation. So, how do you define cutoff? Cutoff is when your IB is 0. For any point in which IB is less than 0, it is cutoff. So, this is your cutoff region. So, your device is cut off, there is no idea. This one is saturation, we have already discussed yesterday, and this is your active region. So, you should bias your device using a DC bias, external DC bias, such that the Q point is somewhere lying here. So, the Q point is this much. Corresponding to this Q point, you will have VCE in this direction and IC in this direction. So, this VCE and this VC, so we write VCEQ and ICQ. So, ICQ is the quiescent collector current, and we define this to be as the collector to emitter quiescent voltage, right. And once we have found out, now what we do with this value of voltage and current if you give in the input side using a DC bias, I superimpose my AC signal over this DC bias, right, and that is what we are trying to do over the period of time, that we are trying to find out a DC signal. So, as you can see from here, the Q point is somewhere well. So, you see this is your saturation region, this is your active region by the definition we are handling, and this below this you have got cutoff, right, and this is the Q point which you see for various values of IB, right. It is actually VBE because IB will depend upon also the value of VBE. Now, IC is by this, and therefore, the slope is equals to minus 1 by RC, and therefore it is known as load line. That you go on changing the load here, right, you go on changing the load here, and you automatically get. So, if the RC value is now smaller, the slope will change drastically, right, the slope will be something like this. Now, it might be something like this, right. So, if you make your VCC larger and larger, the load line will move to the right. If you make it smaller and smaller, it will move to the left. So, it will move like this if VCC is made high, right, and it will move to this side if the VCC is made lower, right. And depending on the value of RC, the load line, the slope of the load line will go on changing, fine. So, we have therefore found out a graphical method by which we can predict what should be the Q point or the bias point where my device should be sitting, so that in the active region, so that a proper amplification is available to me, right. That is very, very important, which I wanted to tell you. This is the, therefore, this is the graphical method of determining the VTC, the voltage transfer characteristics, and this gives me quite a nice idea about, or a decent idea about where should the bias point of the Q or the Q point should be kept in a general. With the same concept we have learned till now, let me show you a proper amplification here. Now, as I discussed with you that this is the common emitter mode configuration transistor which you see, which is this is my NPN transistor. VCE is this voltage is VCE, this is VBE which you see, this is VBE, right, and this is your VCE, right. Now if you there, as I discussed with you, for low values of VBE, typically the device will be cut off because base to emitter junction will not be forward biased. For silicon it is 0.7. So, anything below 0.7 cutoff means this is 0 means all VCC appears across the output voltage, and this is what you see here. So, this part is that discussion which you see. Similarly, if your input voltage VBE is very large as compared to the cut in voltage of the base emitter junction, which is 0.7 for silicon, I would expect to see the transistor to get on. So, I will get from off state. So, this was cut off state, and I will get on state, right, this is the on state, right, and I get saturation here, right, I get saturation. So, saturation is there, and the output voltage will suddenly fall off. Why it will fall off? Because if you remember, VCC is equals to ICRC plus VCE, right. So, if you take it this side and do sort of try to find out the value of VCE, VCE is equals to VCC minus ICRC. So, when your IC is 0, you get VC equals to VCC, and that is what you get here. When you have large values of IC, this quantity becomes large, and what you get is VCE sat, or the saturation value of VCE, which is approximately 0.1 to 0.2 volts typically value. So, this value is approximately equals to 0.1 to 0.2 in saturation, fine. Now, you see, if you bias it here, point A, let us suppose, or you bias it here, let me say here, right, point A and point B, if you bias it, obviously point A and point B will give you a DC bias, external DC output voltage. Point A will give you output 1 and point B will give you output 0, as you can see from the definition of output here. But let us concentrate on the part where this active region is there, active mode is there, right, active mode. In the active mode, if you see, the voltage is drastically falling VCE with the small change in the value of VBE. So, this is basically VCE versus VBE. So, this is the output voltage and this is the input voltage. So, this is my input voltage, right, and this is my output voltage. So, you see this. So, I define my voltage gain AV to be equals to del V out 2 del V in, right, this we have already discussed. So, if you look at point A, my del V out is 0. So, my AV is 0 because there is no change in the output voltage, it is constant independent of the input voltage. Similarly, at point B, my output is constant independent of input voltage. So, in both the cases my overall gain is 0, voltage gain is 0, but the voltage gain in the active mode, which is this one, is pretty high, because you see a very small change in input gives you a large change in the output, right, but the change is what, negative change. So, I get a negative gain sort of concept, which means that for an increase in value of input, I get a decrease in the value of output, right, and the decrease is not equal, but is a very large decrease. So, you get a large voltage gain. So, higher the slope of this curve from Y to Z through Q, more will be the gain, or more will be the slope, and more will be the gain of the transistor. So, if you want to operate the device as an active device, then please operate within this region which is dotted here, and if you do not want to operate and let it work as a digital world, you operate in these 2 positions. So, when you use TTL logic, you use this, right, transistor logic. When you want to use it as an amplifier, you use this, right. So, we have made one thing very clear here, that for sure therefore, that if we have a BJT working in the active mode of operation and I am biasing my device in the active mode, I am surely getting a large level of amplification to me, right, and this amplification will be a linear amplification, right. And I will also like to will show like to you, I like to convey to you why is it like that also. The reason is something like this. So, if the reason is that for equal change in the value of base current, I should get an equal change in the value of a collector current. That is what linearity means, that if I do similar changes in IB, I should expect to see a similar change in IC also, right. So, you see if you change IB by this much amount, right, such that the Q point shifts from here to here on this point and then goes from here to here, right, that the change in IC is linearized. So, this distance is exactly equals to this distance, right, and therefore, we safely say that the amplification is linear in nature. So, the amplification which you find out, amplification is primarily a linear in dimensions or a linear in nature, right. And the reason being that you are able to because the rate of change is almost constant for both the cases, right, and that makes our life easier as far as understanding the graphical analysis is concerned. So, you see I give an input. So, my input will be given. So, let me therefore recapitulate. So, what you do, you first insert a DC source, right, you bias the device where so that it is in the Q point in the active region for amplification purposes, right, and then superimpose the AC signal, right, the AC signal which you want to amplify, right. So, you superimpose the AC signal which you want to amplify. So, given the, so what is the AC signal here, the blue one, if you see here, this is my input AC signal and you are giving it to as VBE. So, I am giving as VBE, base to emitter voltage change. So, I have a DC bias, say 2 volts, and 2 volts DC bias is kept, and superimposed on that I have my AC signal, small signal AC signal, fine. One important point which I should point out here is that there is a limit of the input AC signal. You just cannot give any AC signal you want and it will work fine for the BJT. For example, especially the peak to peak value, right. If the peak to peak value is, suppose you are biasing it Q point here and your peak value is so large that it makes this Q point go somewhere here in the nonlinear region or even here or on the negative cycle somewhere in the nonlinear region or even here, then you enter into nonlinear amplification domain, or the amplification will fall down. Not only that, it will depend upon the value of input, not a good idea. So, you see therefore, we always consider this to be as a small signal analysis, right. What is the meaning of small signal analysis? It means that your input analysis is, what does it mean is, sorry, and it means that the input signal is so small peak to peak that I can sufficiently state that the amplification is linear, because if the if the input signals are too large, then the Q point will move so much away from its basic VCE value, which is kept here, right, which is kept here, that it might even go up to this much point here. Here if you see, it is something like this, it is coming like this, and then it fed like this, and then it became linear, and then it became like this. So if you are somewhere working here or here, it is basically non-linear, and as a result you will get a non-linear amplification. So you need to bias the Q point such that you are just restricting your peak to peak between this point and this point, right. So you should be very careful how you are biasing your device. Depending on that you will get the output. So depending on that you are getting output here, which is 180 degree phase shifted, as well as amplified by a factor which is equals to the value known to you. So what will be the small signal gain which you will get? AV will be equals to VCE, right, divided by VBE. Typically that will be the voltage gain which you will see out of this signal, right. So with this we have understood the basic amplification process of a BJT. So as I discussed with you earlier, also in the earlier module as well as in this module, the most commonly used BJT amplifier is the common emitter amplifier, right. So common emitter amplifier or common emitter circuit is the most commonly used amplifier design. My input signal, as I discussed with you, will always be a sum of the DC bias plus the signal which you apply, right. So Vi is the input signal, will be a sum of the AC signal plus the DC bias. So DC bias will fix up the Q point, and AC signal will be the signal which will be given, which will shift the Q point so that you are able to amplify the signal between input and output. Now the output range is VCE, as I discussed with you, right, and it cannot go beyond a particular region. VCE should also be limited by certain things, just as I should make it a point that VCE cannot be more than, of course, VCC. I will give you an example. Let us suppose you have an input signal which is 1 volt peak to peak, right. You have a V in which is 1 volt peak to peak, your AV is 100, right, and your VCC is let us say 20 volts for a BJT, right. So what will be your V out peak to peak? V out peak to peak, it will be 100 multiplied by 1, which is equals to 100 volts, fine. So your output is 100 volts, but your VCC is only 20 volts. So you see that in no way you can get a 100 volt output. So what will happen is that it will go up to 20 volts, it will then clip back here. This is 20, this is minus 20 or whatever, plus 20, and so on and so forth, or 0, it will go to 0 and will not go further down, right. So you see therefore that the output of a BJT will depend on not only on the gain, small signal gain of the amplifier, but it will also depend upon the VCC which you are using, or the amount of bias you are using to get those functions. The resistor RC has two functions, we have already discussed this point. RC will help you to establish a DC bias. So higher is the value of RC, the slope, higher the value of RC, slope will be lower, but with a negative sign, right, and lower the value of RC, higher will be the slope with the negative sign. The slope is from this side, it is not like this, it is like this. So you will always understand that the slope is negative in a sense. And second is that more important point is that IC multiplied by RC is the output voltage. So no, is the voltage across the value of. So this is the reason why we convert the collector signal current to. So ICRC, right. So VCC minus ICRC is the output voltage, this output voltage. So RC has two collectors or two issues. One is to establish a DC bias at the collector, and the second portion is to convert a signal current, collector signal current IC to its output value voltage V0. This gives me a basic idea about the basic amplification process of a BJT. Let me give you the mathematical treatment here. So if you look very carefully, V0 which is in front of you, right, V0 which is there, right. If you look at V0, this V0 is the output voltage and is equals to obviously VCE must be equals to VCC minus ICRC, remember. We have already discussed this point. By yesterday's talk or previous modules talks, we have seen that IC was equals to IS e to the power VBE by VT. IS is the saturation current, this is the saturation current which you see, this is the saturation current, right. This is the collector current, and VBE is the input voltage for in the case of common emitter, in case of common emitter amplifier, and therefore I get IC SAT to be equals to VCC minus VCE SAT by ICRC. Right, I think this is very pretty clear. So, VCC minus VCE SAT by RC gives you IC SAT. Now, since IC therefore is equal to IS, so VBE is now replaced by VI. We have just discussed this point. Why? Because I can safely say that the total voltage is the sum of the DC bias which you are giving and the AC bias of the signal which you want to amplify, right. So, this is the two voltage sources or two important voltage sources which you are trying to do. So, I get V0 therefore, this statement equals to VCC minus RC times IC. IC can be written as therefore IS e to the power VI by VT, right. Is it okay? Right. Now, therefore, you see very interestingly that the output voltage V0 has an exponential dependence on the value of your input voltage Vi, right, which means that if Vi increases even by a small amount, I would expect to see a drop in V0 by a large amount, because this is an exponential drop which you see. Vt is the thermal equivalent voltage, Vt is the thermal equivalent voltage which is given as kT by Q, and this is equals to 25 millivolt at 300 Kelvin. So, at 300 Kelvin Vt equals to 25 millivolts, right. So, if your Vi is, let us suppose so if my Vi is 25 millivolts, right. So, get e to the power 1, e to the power 1 will be equals to 0, and therefore, I get V0 equals to VCC. Remember, as long as Vi crosses 0.7, I will expect to see V0 to be equals to VCC, because this will effectively go to 0 if not exactly go to 0, right. In the saturation region, which is saturation region after the active region is passed. So, I have got so if you see, if you look carefully, I have got this thing that I have got cutoff region, which is this one, right. This is the cutoff region, then we have the amplification region where the active mode, and I have got a saturation region here. So, cutoff region, active mode and saturation, it will vary depending on the value of VBE which you are choosing. So, depending on the value of VBE, I will be cut off active or saturation region, right. With this knowledge we have gained till now, let me see as what we are looking into. So, we are looking into the fact that therefore, to operate the BJT as a linear amplifier, it must be biased at a point in the active region. We have discussed this point already time and again, that we need to bias it amplify, and then Vi is therefore superimposed on VBE. We again discussed this point in a much more detailed manner. So, I get VCE equals to VCC minus ICRC. So, I get AV to be equals to dV0 dVi, which means the rate of change of output voltage with respect to change in the input voltage for a fixed Vi, comes out to be VBE, right. So, AV is equals to VBE. AV also comes out to be equals to minus 1 by Vt Is e to the power VB by Ic to Ic. Please do it yourself, you will find this answer very straightforward and simple, right. And I will therefore get a negative sign expected also, because the slope is negative, and therefore, I should get a negative gain primarily means with increasing voltage input voltage, the output voltage is decreasing, and that is the reason we define that to be as a negative voltage. Therefore, I get AV to be equals to minus. So, why did you get AV equals to this thing whole quantity? Now, this quantity is basically IC. So, I get ICRC by Vt. So, I get ICRC by Vt. So, this is basically the voltage drop across the resistance at the top, right. This is the resistance RC. So, this voltage is basically the drop at this resistance RC, and that is equals to minus VRC by Vt, right. Now, VRC is equal to VCC by minus VCE. Remember why? Because you had a resistance here and you had this thing, therefore, we get VCC is this one, right, and so VRC is this voltage between these 2 points, and this is VCE, right, VCE. So, I can write down VCC to be equals to VRC plus VCE, fine, and therefore, we can write down VRC to be equals to VCC minus VCE, right. So, in saturation this VCE sat will be typically very small and VRC will be approximately equals to VCC, and you get a very high gain, right. So, but then you have to ensure that you do not go into saturation, because then VCE sat will be typically very small. So, where do you stay? You stay within the active region of operation of the device. So, therefore, I get AV to be equals to minus VCC minus VCE sat by VT, and therefore, the maximum value of AV max is VCE sat. So, if I assume this to be equals to 0 approximately, I get minus VCC by VT as the AV max. So, you see, even if you use a VCC of 1 volt and if you are 25 millivolt you are getting here. So, I will get 1 by 25 into 10 to the power minus 3. So, I get 10 to the power plus 3 here. So, this is basically 1000 by 25, which is basically 40, right. So, even if you do not do much manipulation and incidences, what you get is primarily that the voltage gain of a common emitter mode configuration at T equals to 300 Kelvin happens to be a maximum value attainable is basically 40. But then this is with the assumption that VCE sat equals to 0, which is never. So, actually I will get a drop in the value of VCE in the AV value. In reality AV will be much smaller than 40 even, right, and that you have to take care of when you are actually designing a system. As I discussed with you, therefore, the gain is negative, right, the gain is negative, which signifies that the amplifier is inverting amplifier. So, I have an inverting amplifier available with me and the gain is negative this thing. As a further, the gain is proportional to the collector bias current IC and the load resistance RC. This we have already seen, and you know the reason why the gain is like the collector current and basic reason of this reason is there. Before we finish this module of lecture, let me recapitulate what we did. We had looked into BJT as an amplifier. We have also understood the various parameters which we need to fix from DC domain in order to have a DC in order to bias it in the active region of operation. You cannot bias it in the saturation or in the cutoff region, you have to bias it only in the active region. When you bias it in the active region, you automatically get a very large gain. We also saw that theoretically speaking, the maximum gain available to us in a common emitter mode configuration is minus 40 times, right, provided you are giving a VCC of 1 volt. I get VCC by VT as the maximum theoretical limit which you get in the voltage gain. In reality, obviously you will not get, because VCE sat will never be equals to 0, you will have some finite value and therefore your AV max will reduce drastically in that case, right. So, this takes care of the basic understanding of our design, and in the next turn we will be looking into small signal models of BJT, right. I thank you very much.